we've been doing several videos now to establish a bunch of truths of definite integrals of various combinations of trigonometric functions, so that we will have a really strong mathematical basis for actually finding the Fourier coefficients. And I think we only have one more video to go. In the last video, we said, hey, if you take any combinations of sines where m and n are integers that either don't equal each other or don't equal the negative of each other, that you're going to get that integral is going to be equal to 0. And that if they did equal to each other, well, it's just going to be the same thing as sine squared of some multiple of t. And that actually, over the interval from 0 to 2 pi, is going to be equal to pi. And just to be clear, I wasn't as clear as I should have been in the last video. This is going to be true where m is a non-zero integer. If m was 0, then the inside of this integral would just simplify to 0, and then the integral would be 0. So m has to be a non-zero integer for this right over here to be true. Now what we want to do in this video is do the same thing that we did in the last video, but now do it for cosines. That the product of two cosines where m and n are different integers, or they're not the negative of each other, that's going to be 0. But if they are the same integer and they are not 0, so that will boil down to cosine squared of mt, that is going to be equal, this definite integral is going to be equal to pi. And we're going to do it the same way that we did it with the sines. We are going to use some of our trigonometric identities. And so let's rewrite this right over here, what we're trying to take the integral of. And so this is going to be the integral from 0 to 2 pi. So cosine mt times cosine nt using a product to sum trig identity. And if this is unfamiliar, you can review it on Khan Academy. That is going to be 1/2 times cosine of the difference of mt minus nt. So I could write that as m minus nt, plus cosine of mt plus nt, which I could write as m plus n t dt. So let's think about two situations. Let's think about the first situation. And let me do that dt in blue. So dt. So actually let me now use some integration properties to expand this out a little bit. This is going to be equal to, so I'm going to write this as two different integrals. So one integral from 0 to 2 pi, and I'm going to put the dt right over here, and then have another integral from 0 to 2 pi, and I'm going to throw that dt out here. And so just using some integration properties is going to be 1/2 times this integral of cosine of m minus n t dt, and then plus, I'm just distributing the 1/2 and using some integration properties, 1/2, and now this integral is going to be cosine of m plus n t dt. Now let's think about it. When m and n are integers that don't equal each other, don't equal their negatives. So let's think about m not equaling n, or m not equaling negative n. And we're always assuming that these things are going to be integers, m and n. Well, in that situation, this right over here is going to be a non-zero integer. And this right over here is going to be a non-zero integer. And we've already established that if you have a non-zero coefficient here, that this definite integral is going to be equal to 0. The definite integral from 0 to 2 pi of cosine of some non-zero integer times t dt. Well, that's exactly what both of these integrals are. This is the integral from 0 to 2 pi of cosine times some non-zero integer t, or non-zero integer times t dt. So in this case, where m and n are integers that don't equal each other, or don't equal the negatives of each other, both of these integrals are going to be 0. And then you're going to multiply that times 1/2, 1/2 times 0, 0, 1/2 times 0, 0. It's all going to end up being 0. So that should hopefully make you feel pretty good about the case, this first case. And now let's think about the second case, where m is a non-zero integer, or we could say where m is equal to n. So in that situation, n and m are the same, and they are not equal to 0. So let's just take that situation, especially because when we're looking at Fourier coefficients, we care about the non-negative coefficients. at least the way that we've defined it. So let's just assume that m is equal to n, and that m is not equal to 0. Well, and that would just resolve, that would take this integral and turn it into that integral. Well, in that situation, what's going to happen? Well, this first integral right over here, if m is equal to n and m is not equal to 0, well, it's going to be m minus m. You're going to get, this is going to be 0t. So this whole thing is going to simplify to 1. And then this right over here, you're going to have m plus m. That's going to simplify to 2m. And so let's rewrite the integrals here. This is going to be equal to 1/2 times the definite integral from 0 to 2 pi, 0 to 2 pi of 1 times, I'll write that 1 here, 1 dt, plus 1/2, that's a new color, times the integral from 0 to 2 pi of cosine, let me do it in that same, of cosine of 2mt dt, 2mt dt. So once again, we're assuming m is not equal to 0. This is the definite integral from 0 to 2 pi of cosine times some non-zero coefficient times t. Well, once again, we've established multiple times that this is going to be 0. So this whole second term is going to be 0. And this first one is going to be equal to, I'll just go to neutral color. It's going to be 1/2 times the antiderivative of 1, well, that's just t, evaluated from 0 to 2 pi. So that's going to be equal to 1/2 times 2 pi minus 0. 2 pi minus 0, well, that's just 1/2 times 2 pi, which is equal to pi. And so we have now established this one as well. And now we have a full toolkit. We now have a full toolkit for evaluating the Fourier coefficients, which we will now do in the next video, which is very exciting.